Preparing for a Hadoop Developer interview? You've reached Candy Mentor, and this video is for you. We'll walk through 15 key questions you're likely to face. For each question, you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you explain the Hadoop ecosystem and where HDFS, Yarn, and MapReduce fit? Hadoop solves large-scale data storage and batch processing using commodity machines. HDFS stores data by splitting files into blocks and replicating them across nodes. Yarn manages cluster resources and schedules applications. MapReduce is the original distributed processing model that runs map and reduce tasks close to data. Around that core, tools like Hive provide SQL, Scoop imports relational data, Flume streams logs, and Oozie schedules workflows. I see Hadoop as an ecosystem, not one tool. While answering, focus on Hadoop as a distributed storage and processing ecosystem. Cover HDFS, Yarn, MapReduce, Hive, Pig, Scoop, Flume, Oozie, and how components work together. Question 2. What happens internally when a large file is written to HDFS? When a client writes a file to HDFS, it first contacts the NameNode for metadata and target data nodes. The file is split into blocks, commonly 128 megabytes or 256 megabytes. Each block is written through a replication pipeline, for example, data node A to B to C. The NameNode tracks block locations, while data nodes store actual bytes. Acknowledgements flow back through the pipeline. This design favors large sequential writes and fault tolerance over low-latency random updates. Make sure to cover block splitting, NameNode metadata, data node storage, replication pipeline, rack awareness, client interaction, acknowledgements, and why HDFS is optimized for large sequential writes. Question 3. How does Hadoop handle NameNode failure, and what is the role of high availability? The NameNode stores file system metadata, so its failure can make the cluster unavailable, even though block data still exists on data nodes. In modern Hadoop, high availability uses two NameNodes, active and standby. Shared edits are written through journal nodes, and Zookeeper coordinates automatic failover. The standby continuously applies edits and stays ready. Checkpointing helps compact metadata, but it is not the same as HA. In production, I always treat NameNode HA as mandatory. In your answer, talk about NameNode as metadata master. Single point of failure in older Hadoop. Active standby HA, journal nodes, Zookeeper failover, checkpoints, and operational recovery. Question 4. Walk me through the execution flow of a MapReduce job. A MapReduce job starts when the driver submits configuration, input path, output path, mapper, and reducer classes. Input format creates input splits, and record reader converts data into key value pairs. Mappers process records and emit intermediate pairs. An optional combiner reduces mapper output locally. The partitioner decides which reducer gets each key. During shuffle and sort, reducer tasks fetch and group mapper output. Reducers aggregate values and write final results through output format, while Yarn manages containers and task execution. Be sure to mention input splits, record reader, mapper, optional combiner, partitioner, shuffle and sort, reducer, output format, and how Yarn allocates containers. Question 5. What is the difference between a combiner and a reducer in MapReduce? A reducer produces final aggregated output, while a combiner performs local aggregation on mapper output before data moves across the network. For word count, a combiner can sum counts per word on each mapper node, reducing shuffle volume. The key caveat is that Hadoop may run a combiner 0, 1, or multiple times, so logic must be associative and commutative. I never put business-critical final logic only in a combiner. While answering, compare execution location, purpose, guarantee of execution, input-output type constraints, network optimization, associativity and commutativity requirements, and examples like word count. Question 6. Why is the partitioner important in MapReduce, and when would you write a custom one? The partitioner controls which reducer receives each intermediate key. By default, Hadoop uses hash partitioning, so the same key always goes to the same reducer. I write a custom partitioner when business rules require controlled routing, such as sending records by region, date range, or customer segment. It can improve organization and performance, but a bad partitioner creates reducer skew. The goal is correctness plus balanced load, not just custom logic for its own sake. Make sure to cover default hash partitioning, key distribution across reducers, grouping correctness, reducer load balance, custom partitioning use cases, and risks of skewed partitions. Question 7. How would you solve the small files problem in HDFS? Small files are painful because every file, directory, and block consumes NameNode metadata. Millions of tiny files can exhaust NameNode memory and create too many map tasks. I usually solve it before ingestion by batching events into larger files. For existing data, I compact files into SequenceFile, Avro, ORC, or Parquet. Combine file input format can reduce mapper count, and Hadoop archives can help archival cases. The best fix is designing pipelines around larger splittable files. In your answer, discuss NameNode memory pressure, metadata overhead, why many tiny files hurt performance, and solutions like HAR, SequenceFile, combined file input format, compaction, and ingestion design. Question 8. What is the difference between partitioning and bucketing in Hive? Partitioning divides Hive data into directory paths based on column values, such as date equals 2026-0801. It helps query pruning when filters use partition columns. Bucketing distributes rows into a fixed number of files using a hash of a column, such as user ID. Bucketing can optimize joins and sampling, especially when tables share bucket keys and counts. I use partitions for low to medium cardinality filters like date or country, and buckets for high cardinality keys used in joins. Be sure to explain partition columns as directory pruning, bucketing as hash-based file organization, query performance impact, join optimization, cardinality considerations, and when each technique is appropriate. Question 9. How do you optimize a slow MapReduce job? I start by checking job counters, task timelines, failed attempts, and shuffle metrics instead of guessing. If mappers are excessive, I review split size and small files. If shuffle is huge, I add a combiner, compression, or better filtering. If reducers are slow, I check skew and reducer count. Data locality, container memory, spill settings, and file format also matter. My rule is to identify the bottleneck first. Read, map, shuffle, reduce, or write. While answering, cover profiling counters, data locality, input split size, number of reducers, combiners, compression, skew, memory settings, speculative execution, file formats, and shuffle tuning. Question 10. Which file formats would you choose in Hadoop? Text, SequenceFile, Avro, ORC, or Parquet? Text is simple and readable, but inefficient for analytics. SequenceFile stores binary key value pairs and is useful for intermediate MapReduce data. Avro is row-oriented and strong for schema evolution and data exchange. ORC and Parquet are columnar, compressed, and excellent for Hive or Spark queries that scan selected columns. In production, I usually prefer Parquet or ORC for analytical tables, Avro for ingestion streams, and compressed text only for simple landing zones. Make sure to compare row versus columnar formats, compression, splittability, schema evolution, Hive and Spark compatibility, analytics performance, storage efficiency, and practical selection criteria. Question 11. How would you handle data skew in a Hadoop job? Data skew happens when some keys have far more records than others, causing a few reducers to run much longer. I first confirm it through reducer input counts and task duration. For hotkeys, I may add salting, perform two-stage aggregation, or use a custom partitioner. A combiner helps if aggregation is possible. Sampling can reveal bad key distribution early. The trade-off is complexity. Salting improves parallelism, but requires a second step to merge partial results. In your answer, discuss identifying skew through counters and reducer times, hotkeys, custom partitioners, salting, two-stage aggregation, sampling, combiner usage, and trade-offs. Question 12. What is Yarn, and how does it improve Hadoop compared to Hadoop 1.x? Yarn is Hadoop's resource management layer. In Hadoop 1.x, MapReduce handled both processing and resource scheduling, which limited scalability and supported mainly one compute model. Yarn separates those responsibilities. The resource manager allocates cluster resources, node managers run containers on worker nodes, and each application has an application master. Because of this, MapReduce, Spark, Tez, and other engines can share the same cluster. Yarn made Hadoop more scalable, flexible, and efficient for mixed workloads. Be sure to mention Resource Manager, Node Manager, Application Master, Containers, separation of resource management from processing, multi-engine support, scalability, and better cluster utilization. Question 13. What is the difference between managed and external tables in Hive? A managed table means Hive owns both metadata and data. If I drop it, Hive removes the metadata and deletes the underlying data from the warehouse location. An external table means Hive only manages metadata. The data stays in an external HDFS or object storage path after drop. In production, I often use external tables for shared raw or curated datasets because multiple engines may access them. Managed tables are cleaner when Hive fully owns the lifecycle. While answering, cover ownership of data, metadata in Metastore, drop behavior, data lifecycle, warehouse directory, external locations, governance implications, and common production usage. Question 14. How do Kerberos, Ranger, and HDFS permissions work together in a secure Hadoop cluster? Kerberos handles authentication. It proves who the user or service is using tickets and principals. After authentication, authorization decides what that identity can access. HDFS permissions and ACLs provide file system level control, while Apache Ranger centralizes policies for HDFS, Hive, HBase, and other services. Ranger also gives auditing, which is critical for compliance. I think of Kerberos as identity, HDFS permissions as base enforcement, and Ranger as centralized governance with least privilege policies. Make sure to describe authentication versus authorization, Kerberos tickets, HDFS ACLs and POSIX permissions, Ranger policies, audit logging, service principals, and least privilege access. Question 15. Design a Hadoop pipeline to ingest daily relational database data and make it queryable in Hive. I would use Squoop or a modern ingestion tool to pull incremental data using a timestamp or primary key watermark. Raw data lands in an HDFS staging path, preferably an Avro or Parquet after validation. Then I load it into a Hive external table partitioned by business date. An Oozie or Airflow workflow handles scheduling, retries, and dependencies. I also add row counts, checksum checks, late arrival handling, and alerts. The design should be repeatable, auditable, and recoverable. In your answer, talk about Squoop or ingestion alternatives, incremental imports, landing zones, file formats, partitioning by date, Hive external tables, validation, scheduling, retries, and monitoring. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.